Hey, what's up everyone? So in this video we're going to do a problem where we find the abundance of two isotopes of an element given the following information. So we're going to be given the mass of each isotope of the element, and we're also going to be given the atomic mass of the element. So if you'd like to, please feel free to watch my video on isotopes. There's some things I'm going to be going over in this video that you won't really necessarily be able to understand unless you know a couple of things about isotopes already. So in other words, there's some information that you should know already before you watch this video, the one you're watching right now, and all of these things are covered in my video on isotopes. So please feel free to check that out if you're a little unfamiliar with isotopes, or if you'd like to sort of reinforce the information that you already know about isotopes. So, alright, let's get into the problem. So the problem says silver has two naturally occurring isotopes, and those are silver 107 with a mass of 106.905 AMU, and silver 109 with a mass of 108.905 AMU. It says that the atomic mass of silver is 107.870 AMU, and it asks what are the relative amounts of silver 107 and silver 109 in nature. So in other words, what are the percent abundances of these two isotopes? What are the fractions of those isotopes that exist in nature? So this is the kind of problem where, if you don't know what you're doing, if you see this on a test, you might tend to sort of panic a little bit and like, oh man, how do I even begin to solve this? But there's definitely a way that you can solve this. It's a little complicated and it might require you to think outside the box a little bit, but nevertheless, it all makes sense in the end. So let's figure this out. So again, we have three important pieces of information. We have the mass of silver 107, the mass of silver 109, and we have the atomic mass of silver. So the main formula that we're going to use here, one of the main formulas that we're going to use here is for the atomic mass of an element. So remember, the atomic mass of an element, the way that we get that is we take a summation. That's what the sigma means. It's a summation of n isotopes. So n is the number of naturally occurring isotopes that the element has. And the summation, the terms that you add together are the fractions of the isotopes multiplied by their respective masses. So what does this look like with our numbers? Well, for silver 107, we would take the fraction of silver 107, which I'm just going to abbreviate F107, F107 times its respective mass, that 106.905 AMU. And we're going to add to that the same term for silver 109, the fraction of silver 109 times its respective mass, 108.905 AMU. So it says the summation of these two terms is equal to the atomic mass of the element, which for silver is 107.870 AMUs. So this is our formula for atomic mass. But unfortunately, we can't use this equation alone to solve for each of these terms. We only have one equation and we have two unknowns. So in other words, we need another equation that involves both of these terms in order to be able to solve for them. So the way that you get your other equation is, again, like I said, you have to think outside the box a little bit. But it has to do with the very, very first sentence of the problem. Let's go back to the problem real quick. It says silver has two naturally occurring isotopes. So that means that whatever those percent abundances are of those two isotopes, they're going to add to 100. So let's write that down. So there it is. Silver, in other words, the percentage of silver 107 plus the percent abundance of silver 109, that has to be 100%. And to convert those percentages into fractions, basically all we have to do is divide by 100, because that's what a percentage is. It's just the fraction multiplied by 100. So in other words, if we divide this whole equation by 100, we're going to get the fraction of silver 107 plus the fraction of silver 109 is equal to 1, which makes sense. All of the fractions added together should equal the whole, which is 1. So these are our two equations that we're going to use to solve for both of these unknowns. Now the question at this point is, how do you want to go about solving for these unknowns? There's a couple of ways you can do so. One of them is called substitution, and basically what you do is you solve for one variable in one of the equations, and then you plug your expression for that variable into the other equation. That's one way you could do it. Or you could use what's called Cramer's rule, which involves matrices, and I'm not really It's not really my intention to teach matrices in this lesson, so we're not really going to use that method. But the method that I'm going to use that I really like is called the elimination method. So the way that the elimination method works, I mean, we're digging back to sort of, the finer points of algebra here. But the way that you use the elimination method is what we're going to do is we're going to multiply one of these equations by a factor. And we're going to choose our factor such that one of the variables is going to be eliminated when we add the equations together. So that's what we're doing. We're multiplying by a factor and then adding the equations together. So let's do that. So the factor that I'm going to choose, again, I'm trying to eliminate one of my variables. So I'm going to multiply this bottom equation here. I'm going to multiply that by negative 106.905 AMU. Okay? So if I multiply the equation by this term, that means I have to multiply each of these individual terms by that negative 106.905 AMU. So starting with the F107, if we multiply that through, that'll be negative F107 times 106.905 AMU. If we do the same thing with this term up here, that's going to give us F109 times 106.905 AMU. And then if anything multiplied by 1 is simply whatever that thing is, so that's going to be negative 106.905 AMU on the right-hand side of the equation. So you may be asking yourself, well, why did I choose this term? Well, the reason why I chose this term is so that when we add the equations together, the F107 terms, the fraction of silver 107 terms, those are going to cancel out when we add them, right? So we're adding the two equations. This variable cancels out. We're left with one variable and one constant. So if we add the left-hand side of the equation together, we will get F109 times 2.000 AMU. And then we add the right-hand side of the equation together. That's going to give us 0.965 AMU. So to get the fraction of silver 109, you simply divide that 0.965 AMU by 2 AMU, and that will give you your answer, which is 0.482. So this is how you get the fraction of silver 109. And now that we have the fraction of silver 109, we can easily get the fraction of silver 107 simply by subtracting 0.482 from 1, which again is what the fractions should add up to. They should add up to the whole. So we take 1 minus 0.482, and that gives us 0.518. That is the fraction of silver 107. And if you want to find these fractions in terms of percent abundances, all you have to do is just multiply those fractions by 100%, and that'll give you the percent abundances. So this means we have 48.2% silver 109 and 51.8% silver 107. All right, so I hope this video helped you out a little bit, and have a good one.